start on the fuel booster and the exhaust valve. So I can see there's a question here. The FIVA spool will move up and down depending on RPM engine cycle. Yes, indirectly. The FIVA, if we look at the PowerPoint presentation, if you can see just about, if you look here, we zoom in, the FIVA will move according to the set point, i.e. the signal from the control signal shown in blue here. So as the set point, the red line just visible behind the green one, as the set point is moving or giving a signal to move, then the control signal will be sent to the FIVA to move in this direction. Remember, from left to right, there is no movement. Up and down is the movement of the main spool. So you can see here, we have a prepare to open. Then we have, we can see here, we have a prepare to open, no movement. Open exhaust valve, so synchronize to open, no movement. Prepare to close, no movement. Synchronize to close, no movement. Prepare to inject, no movement. Synchronize inject, no movement, and so on. So every position, every flat line shown here is no movement of the main spool. Every up and down movement is the position of the main spool within the housing. Okay, so of course, indirectly, yes, the RPM and load or engine cycle will affect it because, of course, the engine is rotating, the crankshaft is rotating, the piston's going up and down. This is the set point that is generated from that within the system, within the control system. Okay, you have your layout, your engine layout, your 0 to 100% MCR. This is programmed, this is written in as an algorithm into the engine control system. Okay. Hopefully I didn't overcomplicate a simple answer. So looking here, we can see that we have the, excuse me, burst log for CCU number 2. And we can have a left-hand side on the axis here, we have the bits, which can equate to millimeter positions of the movement of the FIVA. And along the bottom, we have a time frame. In this case, it is, we can see 5 seconds. This part here is the marker. This is telling us where the burst log was taken. And then we have a time frame before and a time frame after. Approximately 2.5 seconds before and after, so giving us this 5-second window. That is more than enough due to the accuracy and the timing. So we have an accuracy from the tacho at 0.25 degrees and an accuracy of the FIVA valve at 0.5 millisecond. So 5 seconds is an age to identify what was going on. So we can see here this is a manual dump, so we know that we're having a record of a manual dump, so we have a record of a functioning system. So we can see that we have a nice set point, a nice control signal, a nice feedback signal for the FIVA loop or the FIVA cycle here, and we have a nice feedback from the fuel booster and a nice feedback from the exhaust valve. So this is a good one to look at, and what we do recommend is when you are on board, whether your engine is new or not, that we recommend at certain loads and speeds that you would take a log of each individual unit. So you would just go to your maintenance on your maintenance folder and your troubleshooting on your Mod B, and then just say log manually, and then just press 1, 2, 3, 4, 5 and up to how many units you have, and it will automatically log there, and then you have a reference point. Do it at specific at different engine loads and speeds, so you have a nice range of baseline data. Then you can extract the data onto a USB stick and put it into your laptop, and then using this program, which you can see here, the LDE plot program, you have a more user-friendly interface for reading and understanding your hydraulics in unit events. Here we have now a hydraulics in unit with the LFI and LVA. So we can see they have the LFI, electronically controlled fuel injection, and ELVA, the electronically controlled valve actuation. So two separate valves for two separate functions. So this is for a larger engine. So it's for the G engines, the large stroke I mentioned before, and what Mr. Francis talked about on the first day. So the huge G engines, G95 engines, we have split up. So we have the signal to and from this, sorry, signal to and from the ELFI, and we have a signal to the ELVA. There's no feedback from the movement of the the ELVA, because of course it is either open or closed, but you still have the feedback sensor on the exhaust valve itself. So we have inside split up, so you can imagine that we have still a main spool and then some ports to open and close, i.e. pressure to the booster or pressure from the booster. Here we have pressure to the actuator or from the actuator. So two positions, one pressure, one drain. The pilot valves we have in service, we have the Parker, we have the Moog, and we have the Nabtesco. The Nabtesco pilot valve is of course on the Nabtesco FIVA valve, and the Parker and the Moog are the two designs that we use on the MAN FIVA valve. Function is the same. You get a signal in and you have a movement of a pilot spool inside the silent valve here. So gentlemen, are there any questions to do with the FIVA? So now we're going to have a look at the fuel oil booster. Here we can see we have the MC fuel pump. Here we can see we have the ME fuel oil booster. So a lot of moving parts, quite intricate and sometimes susceptible for sticking and giving us an inadvertent injection. Here we have very few moving parts. We have the hydraulic piston, we have the top cover, we have the fuel plunger and umbrella seal, we have the suction valve. That is it. So inside the suction valve, we of course have some moving parts. It's the same principle, same design as it always has been as a suction valve, needle and spring to allow the 7 to 10 pressure fuel oil pressure in the top part, and we have our hydraulic power supply pressure on the underside here. Okay, as you can see from the design drawing here, or design image here, that we have the plunger and umbrella seal, and we have the hydraulic piston, and they are separate. They are not mechanically connected. They are resting on top of each other, and the constant pressure on the top side of the plunger and umbrella seal, and the residual pressure and constant pressure depending on the operation from the hydraulic power supply system is keeping them together. So looking at the fuel oil booster, so we can see that we have the FIVA valve down here, signal to the FIVA from the control system CCU, moving the spool in the opposite direction, allowing a flow of pressurized oil through the port to the fuel booster, forcing the hydraulic piston up, and at the same time forcing the fuel plunger in the upwards motion, charging the fuel oil pressure in the top cover to give us a fuel injection to the common slide fuel valves now. Okay, when we've done this, of course this will close or go to the center position. We will drain from the underside of the booster, and the return of the plunger and the piston is assisted by the constant fuel oil pressure at the top part of our fuel oil booster, i.e. the top cover. Looking at the design drawings, we can see here that we have the top cover, we have the suction valve, we have the top cover and the suction valve shown here. Inside the top cover we have the plunger, so the top cover and the plunger act as the plunger barrel if you compare it to the MC fuel pump. Then we have the main housing here. And we can see as we follow the plunger down, we have this conical form, this umbrella seal, and the umbrella seal, or the conical shape of that, is where the feedback sensor is